Well, hello. My name is Dan Hollow. I'm the Rocky Mountain Regional Manager for TESCO. And today we're going to do a presentation on simulating real-world metering conditions. So I'm going to be kind of jumping back and forth between PowerPoint and a software application called Test Manager, TMA. And so we'll get going. If anybody has any questions, you can unmute yourself or use the chat, but it's a little more difficult for me to jump back and forth to the chat and because of the way I have to share my screen and jump back and forth between applications. So it might be better if you just unmute, ask your question, and remute again. Does everybody know how to do that? You hearing me?
Tell Dan, they don't talk much.
Okay.
Yeah, I'm sure they know how to do it, so.
All righty. So you can see my screen right now in slideshow mode. Hello, who is this I'm speaking with, by the way?
This is Rob Pierce with the league.
Hi, Rob. How are you?
I'm doing good. You've been shoveling snow, have you?
No snow, but brutal cold.
Well, come on out to Lincoln. We'll help you with a shovel.
We're supposed to get a little bit this weekend, but fortunately for us, most of the snow falls in the high country in the mountains here in Colorado. And here on the Front Range, we get spared a lot of the snow.
Well, better for skiing, I guess. With that, I think we're ready to go, Dan.
All righty. All right. I introduced myself here as our opening slide. We're not going to spend much time on my biography here, but I've been in this industry 32 years now, and in the tech industry for my entire adult life since 1980. So you can run the math on that one. I've worked in different industries before I came into the utility industry for a company called Aptech back in 1989, I believe it was, or 88, sorry. I started out as a test department supervisor and then accepted a sales position in 1992 and been with quite a few companies since then, been acquired a couple of times, so I've been around a bit. And this is my first time being on the testing end of meters. My background was always in communications, data acquisition, data management, web presentment, complex billing, that kind of thing. And since starting with TESCO, I've got to see what it's like to test meters and current transformers and so on. So what we're going to do here today is we're going to subject electric meters to non-nominal conditions, more similar to what a meter would see in the real world as opposed to the ideal conditions that you see when you run a meter accuracy test on your test board. So what we're going to do is we're going to generate conditions that occur in the real world like sags and swells, look what kind of impact that may have on the AMR-AMI module. We're also going to look at what impact or what registers with the meter. So if you have meters that are programmed to register sags and swells and you've defined a threshold for what constitutes as a sag, what constitutes as a swell, and you go over that limit, let's say 6 volts over, it's going to see that as a swell. You go 6 volts under, it's going to see that as a sag and so on. And that should be logged in the meter's event log or history buffer. Also going to subject the meter to phase angle variances representing, 0.5 power factor lagging or 0.5 leading and so on. We can modify the line frequency from 60 hertz to 45 hertz all the way up to 65 hertz, see if it has any effect on the meter. Meter should operate at those frequencies. We can drop a phase of current that would simulate an open CT or some wires between the CT and the test switch being open wires, pinched wires, that kind of thing. We can introduce harmonics onto the fundamental 60 hertz waveform and see what the results are going to be. See that the meter may have a total harmonic distortion or THD threshold set up in it, and see if it exceeds that threshold. Also, the same is true with your AMI systems. Your AMI head-end software should be able to connect to a specific meter that's in one of these test boards like I'm using today, and see the conditions that I'm subjecting the meter to, whether it be harmonics or poor power factor or sags and swells in voltage or dropping a phase. Your head-end software for your AMI system should also see the effects that I'm exposing the meter to using this particular test board. We can also do disconnect testing on this particular test board. And we can apply back voltage to make sure that the service disconnect switch in the meter does not close back in when it sees back voltage on the load side of the meter. So we can do all kinds of different things that simulate real-world metering conditions that normally you don't do or try to do or can't do because of your test board in the shop. So it allows you to see if your meter is programmed as you expect it to be from the manufacturer. It allows you to see if your head-end software can see the conditions you're exposing that particular meter to that you're running these kinds of tests on. And real quick, I'm just going to open this little hyperlink down here, hopefully. There we go. I don't know if you can hear it. That's interesting. Well, anyways, I'm not sure why I'm not hearing it. I don't imagine you're hearing it. This was pre-recorded, so I haven't had a chance to see why it's not coming through. Did you happen to hear that? No? Okay. Well,
I didn't hear it.
You did?
No, I did not.
Okay, yeah, not sure what's going on there. That's like a little pre-recorded video I did, and apparently the sound is not coming through this WebEx. But that's the device we'll be using today. I've actually got a different meter plugged in there right now. So we're going to move on here. And so that's the device we're going to be using to do these. I don't necessarily want to call them tests. What we're really doing is subjecting this meter to different non-nominal conditions, things they would see in the real world as opposed to nominal perfect conditions that you would normally have a meter see when you're doing an accuracy test or something like that. So now I can set the voltage to a sag here, and I'm going to have to unfortunately jump back and forth. So we're going to share the application software. So here's our application software. This is TMA that you're seeing right now, hopefully. And right now we've just got voltage applied, and we've got 120 volts. This is a 9S meter. This happens to be a Itron Centron. And it's got the typical test voltage here for full load testing. I could set the current to whatever. I could set the voltage to whatever. I can go into the field and just change the voltage manually just by going in there and changing it to something else. So I could go in and say, yeah, it's 125, and then now the meter is seeing 125. And unfortunately, you can't see the LCD display on the unit itself because I have to have my webcam 4 inches away from the display for it to not look washed out. So unfortunately, I'm only going to have static pictures of the display on the unit to show you. Plus, jumping back and forth between the webcam 4 inches from the unit and getting back to this is kind of a practical nightmare. So you can also go in here and use these little black buttons to change the phase angle, change the current, or change the voltage. So now I can put it back down to nominal, or I could go and hit it and go below. So now we're down at 115 volts. So I can sit here and just lower this thing as much as I want, or raise it as much as I want, simulating sags and swells. So you can see the voltage changing there. And I will show you a representation, a snapshot, a picture I took with my phone of the screen. I can do the same with the current. I can change the current in 1% increments to anything I want. This is a class 20 meter, so obviously I can't go above 20 amps. I can sit here and just change that current to whatever I want, just going up in 1% increments. Same with the phase angle. I can change that in little 10-degree increments. So now I'm going leading power factor. I can go the other way and do lagging. And we can go back to unity power factor or power factor of 1. So it allows me to go in there and manipulate the current, the voltage, and the phase angle very simply with these buttons, or I can just type the values that I want in there and do it that way. So we will go back to the PowerPoint. Sorry, this is a little cumbersome. We can also lower the voltage on the meter to a point at which the meter stops functioning, which would simulate a brownout condition. I found on the majority of meters, in the case of this 9S meter, the nominal operating voltage is 120 volts AC. I can drop this meter down to about 90, sometimes 85 volts before the meter will stop functioning. You could also bring the voltage back up after, you know, the display usually goes blank or freezes once you go below the operating voltage at which the meter can operate. It'll either freeze the display or the display will just go blank. And then you can bring the voltage back up slowly or all of a sudden if you want, and make sure that the meter starts functioning again, and that if you've got an AMR, AMI module, that it's still functioning as well as the meter. So they should both recover after you simulate a very severe brownout condition. Hopefully you never experience one like that on your distribution system. Same going with the maximum voltage. You may or may not want to put this one to the test. If you have an auto-ranging meter, you really don't have a lot to fear because auto-ranging meters usually do 120 to 480. So this particular device will not exceed 480 volts, so you won't actually blow up the meter and test the limits of the auto-ranging power supply in a meter. But you can do those kinds of things. If you want to fry a meter, that's not usually recommended, but a lot of times when a utility is doing first article testing on a meter, they might want to really beat up the meter, run it through the paces, give it a lot of real-world conditions, and see that that meter functions properly across the voltage range, that it sees the sags and swells, that it sees the power factor changes, and so on. So basically, you're really running rigorous testing on the meter to make sure it does what it should do. So I can, again, change the phase angle to anything I want, move it around, showing you with those little black buttons, or I can go ahead and just type in the phase angle variance I want the meter to see, and then I can set it back to a power factor of 1. I kind of did that briefly. You can also go in there and change the line frequency, so we'll go ahead and do that real quick. So up at the top of the screen, you'll see there's the line frequency. It defaults to 60 hertz, of course, but I could go in and say, well, there's 65 hertz, and now this meter's seeing 65 hertz. Or I could go down to 55 hertz, or all the way down to the minimum, which is 45. So now this meter is seeing 45 hertz. Since a lot of these meters are sold into countries that have 50 hertz systems rather than 60 hertz systems like the U.S., they should all operate just fine at 50 hertz. Will they operate fine at 45? I've never found one not work, I'll put it that way. So you can do things like that as well. You'll notice when I change the phase angle, I'll go ahead and put that back to 60 hertz. Like I say, if you change the phase angle, we'll go the other way. Oops. So there's power factor of 1. So on the front of the display of the device, you'll actually see the voltages for each phase. You'll see the current for each phase. You'll also see the power factor. So right now, it's reading 0.6 power factor on the instantaneous screen on the device. Like I say, it's difficult to jump back and forth to see that because you have to be about 4 inches from that LCD screen to get a decent picture of it. So we'll return this back to unity power factor. And you can see over there on the right that you are changing it. You'll notice that all the phases of current are in phase with each other. And that is because this is a series parallel test board. We also make, obviously, true 3-phase test boards. So on a series parallel board, you cannot change the current on each phase to a different current. So I couldn't set this at 2.5 amps and then set this at 5 amps and set that at 10 amps on this meter because this isn't a true 3-phase test board with independent control of each phase of current and independent control of each phase of voltage. So the voltage will always be the same for all 3 phases, and the current will have to be the same for all 3 phases. That's because it is a series parallel as opposed to a true 3-phase. So some of you out there might have true 3-phase boards. Some of you may have series parallel boards. Some of you may not be sure. If you want to know if you have a series parallel board, just put in a 9S meter and go to your vendor software, whoever that might be, you know, Honeywell, Landis & Gear, Itron, Census, whoever. Go use their software, read the meter optically, or you can also do it through your AMI head-in. It's just easy to do it optically. And then you can see if all 3 phases are lined up at 0 degrees, all 3 phases of current, or if those 3 phases of current are all out of phase with each other. And that is what you would see on a true 3-phase board, whereas on a series parallel board, you will see that all 3 phases of current are in phase with each other. That's just a little tidbit of information and the differences between series parallel and true 3-phase boards. So now we'll jump back to the PowerPoint, try to stay on track here. And again, when you change from 45 hertz to 65 hertz, you shouldn't see any difference in the operation of the meter. If you do, that's a problem. You also have the ability, now on this board, I can disable phases that would represent the meter losing a phase. So I can disable phase A or phase B or phase C. And in the real world, that would be representing a CT going bad, have an open winding on the secondary. So if you had an open winding on the secondary of any CT on a 3-phase service, I can simulate that by dropping that phase. It could also be the wiring between the CT secondary and your test switch. You could have an open wire, a pinched wire that got severed. So this would simulate the losing of a phase. And again, your meter should see that, and it usually gets logged in the event log, history buffer, whatever you want to call that. They have a couple different names. You'd also see that if you were reading the meter in this test board real time with your AMI head-end software and you drop the phase, you should see that represented in your AMI head-end software. Then we can re-enable it, and then I'll have to swap meters to do this next test. now we're back here. We're going to turn on the load. Like I say, I could make the load whatever I really want it to be, as long as I don't exceed the maximum. If we're to try to go in and exceed the maximum, I'll go ahead and do that on here just so you see what happens. So obviously on a class 20 meter, I can't put 25 amps on it. So if I attempt to turn on the load, we're going to get an error message saying, sorry, no can do. You've exceeded the class of this meter with regard to the current. So I've gone past that class 20 to 25 amps. It will not let me do that. So I can go there and just do 2.5. Oh, sorry. And then turn on our load. So now we've got 120 volts, 2.5 amps. These are the nominal conditions for a full load test for a class 20 9S meter like we have here. So now I can go in here and I can hit this button and I can pick any phase I want. So I can drop phase C or I can drop phase B. So I'll go in here and drop a phase. Oh, you have to have the load off. So now I can go ahead and drop that phase, turn the load back on, and now phase B has no current on it. So basically I've simulated either a CT on phase B going bad or the wires between that CT and the test switch being open. So that's a nice little test you could do, and I could, drop these phases ad hoc. I could drop 2 phases if I wanted. So now I've only got current on phase A in this scenario. I'll go ahead and turn the load off, or restore everything back to 2.5. And there we go. So now I'm going to have to actually swap meters for this next test. So what I'm going to do on this next test is put in a 2S meter. That would be your typical residential house meter. And I'm going to do that in the board right now. So this is what the screen looks like on the front that we can't see from any distance greater than about 4 inches, or it's just a bright light. The LCD screen on this unit is extremely bright. I can see it from here, and I'm about 6 feet away from the unit right now. But when you try to take a still picture of it with your camera phone, or if you try to use a webcam on it from any distance, it's just a bright light. So you have to get right up on this display about 4 inches away to be able to video it with a webcam or take a still picture with your camera phone. So I just wanted you to see what that display looks like on the front of the unit. As you can see here, I've got 5 amps of current on each one of them. This is a 9S meter at the time I did this particular test, and I was dropping phase B. So you can see I got 5 amps on A and C and 0 on B. So this was the drop of phase, simulating the CT with an open secondary or bad wiring between the CT and the test switch scenario. But we're going to go back up to this slide, and we've got that Form 2S meter in there now. So we could, on the previous meter, I could select it. Sorry, I kind of jumped ahead of myself. But I could change it to whatever. Go back to the software. Jumping ahead of myself here. So I've got my 9S meter back in there. Turn on the voltage, turn on the current. So I can go over here and pick a phase and throw it 180 out. And now you can see there's your current representation. Here is red dotted line is A, yellow dotted line is B, blue dotted line is C. I just took A and I threw it 180 degrees out of phase with B and C phase. This represents somebody reversing the CT secondaries at the test switch. So if somebody goes out there and wires up the 3 CTs for a 3-phase 9S type service like this, and they inadvertently swap the CT secondaries at the test switch, they would be 180 out of phase. I just simulated that condition here. Your meter should recognize that being 180 out of phase, as well as your AMI head end. So then I can restore it back. So now all are back in phase again. So that's a nice little test to do. Again, want to make sure that your meter recognizes that you got a phase that's 180 out from the other phases, and that your AMI head end software also recognizes that phase being 180 out. So we're going to go ahead again, and sorry I jumped ahead of myself. We're going to go ahead and put that 2S meter in. All right, so we'll just go up here and we'll tell it, well, we no longer have a 9S, we have a 2S meter, just a regular single-phase meter. It defaults to test amps, which in this case is 30 amps, but I can change that current to anything I want, all the way up to 50 amps. So we'll put 50 amps on it just for fun. That's the maximum this board can put out, which will allow you to test your Class 320 meters. So we've got 240 volts at 50 amps. And like I showed you earlier, we can alter the voltage, the current, and the phase angle by these amounts: 5-volt increments, 1% increments on the current, and 10-degree increments on the phase angle. So I can go ahead in here and flip these around to whatever I want. We're going to turn the load off. We're going to start at 0. So now this is what you would typically see on a real single-phase service. When I start to tweak this around, doesn't matter which direction I go. Now I'm 180 out of degrees from what I should be on this single-phase meter. So now when I look at the meter and I look on the LCD display of the meter, the worm gear or the indicator, the arrow, they're different on each meter, that indicates the direction of current flow is flowing backwards. This simulates a customer situation where they have solar panels on their roof and the customer's not home and they're using very little energy, and the solar panels are putting out received power back out onto the utility's distribution network. So bottom line is this simulates a net metering scenario where the customer is actually generating more power with their solar panels than they're drawing from the distribution system. So this is all received energy, and the current's flowing backwards. The worm gear on the meter is pointing in the opposite direction than it would normally be, and this simulates a net meter situation. So if you program a meter for delivered, received, and net, you'll have 3 buckets, 3 registers within the meter, One is storing the delivered energy that the utility is supplying to the customer. One is storing the received energy that the customer is putting back out onto the grid with their solar panels. And the last register or bucket is the difference between the two. And that's usually how customers that have solar panels are being billed, is on the net metering. Then we can throw it back into phase, representing nominal conditions out there at the customer site where they're using power and they're not generating any power. All right, move on here. So another thing we can do here is subject the meter to harmonics. So we can introduce harmonics onto the 60 hertz fundamental waveform and see what effect that has on the meter, or it may have an effect on the AMI module. It may have effect on an AMR type module. So you can subject that meter to a lot of harmonics and see what the effect is. It should be seen both by the meter. If you exceed a THD threshold that may have been programmed in the meter, you're also going to see that on your AMI head-in. In the case of power line carrier AMI systems, whatever that may be, a TWAX, a Canon, trying to think of the other ones that are out there anymore. But any of the power line carrier solutions out there, the old Turtles, the Landis & Gear Hunt Turtles, if you subject a lot of harmonics to those types of AMI modules, they may not be happy with that, and they may not work properly because you're putting out a lot of harmonics onto the fundamental waveform, and we're going to go ahead and simulate that right now. All right, wrong thing here. Let's try that again. There we go. All right, so right now this is just a residential meter, but it doesn't matter. We can introduce harmonics onto any form factor of meter. So we're going to go ahead and go from sinusoidal. We're going to shut off the current to do this, and we're going to use, these are canned harmonic waveforms that are part of the ANSI C1220 waveforms. I like this one, but there's a whole bunch of them here. It's pretty ugly. So we're going to go ahead and put that on all three phases. So you can see that that sine wave doesn't look so pretty anymore. And, well, apparently this one, oh, I'm at 50 amps. That explains it. We'll drop down to a lower current. All right, try that again. There we go. At a lower current, it has less problem. As you can see, that waveform is a long way from sinusoidal. That's some pretty ugly harmonics. This type of harmonics, this extent of harmonics, could have significant impact on the meter, could have significant impact on the AMI module, whether that AMI module is power line carrier or radio frequency, RF. I go in and I could change it to something else and choose a different harmonic content from the C1220 waveforms. Turn on the, oh, must be the same, so I apparently didn't do the same one here. There we go. So now that's what the current waveform looks like. As you can see, that is less than ideal. These are terrible harmonics that in a lot of cases would affect obviously the customer, possibly the meter, and also the AMI modules. So you can go in there and simulate some really nasty harmonics and see what kind of impact that has on the meter, on the AMI module, and also verify that the AMI head-end software is seeing maybe a total harmonic distortion threshold exceeded. So we're going to go back to sinusoidal. There's all different options here. You can even do some custom user-defined options. You know, you do the, the 3rd, the 5th, the 7th, the 11th, whatever. So now we're back to, hang on. There we go. Now we're back to normal, no harmonics, back to ideal nominal conditions. So this one, unfortunately, is another case where I really can't set up the webcam for you to see it unless I put my webcam right up on top of it, and at that point, the only thing you would see is the LCD screen on the device. This is a test that cannot be performed with the software. It has to be performed using the keypad on the front of this test board and looking at the display. But I have a Form 2S in this event. It's an Aclara I210 Plus with a service disconnect switch in it. And I can go ahead and open the contacts and close the contacts with the device we have called the safety disconnect device that works through the optical port on the meter. I can also put back voltage on the meter and then try to close those contacts of the service disconnect switch in this meter, representing someone that has a backup generator on their house, or maybe they ran an extension cord over their neighbor's house because their power had been shut off, and they try to hook it up to their breaker panel, or maybe they even go into the meter socket and hook it up to the load side on the meter and try to backfeed the service because they've been shut off for non-payment. And if they do that, you don't want that service disconnect switch to close back in. So here is the unit, and at the moment I have that I210 Plus Aclara meter in there, and I have our 1039 safety disconnect device put on the optical port. It's a very simple device. You just put it on the optical port of a meter. You program the passwords of your meters into this device with a piece of software we provide and a USB cable. And once you program the passwords into the device, that's it. That's the last time you have to use that software, and the passwords stay in this device. Right now, I had already hit the Open Contacts button. If you can look right down here on the button, you'll see jaw 2 and jaw 4. Those LEDs are off. That means these contacts in that meter are open, or customer power off for non-payment. Now, as you can see here, I've hit the close button on this device we make, and now the LEDs on both jaws are on, indicating there's physical contact in the disconnect switch in that meter, or customer power on. If I were to go in there, as you can see, right now I've got 30 amps, 240 volts. The back voltage is disabled. We've got buttons down here on the screen of the unit where we can enable or disable the back voltage, representing somebody with that generator on, or somebody running a cheater cord from their neighbor's house because their power's been shut off, and you don't want the meter disconnect switch to close back in with that back voltage present on the load side. So now, as you can see, here's another picture of the LCD display on this unit, and I've enabled the back voltage. So if I were to hit the close button on that safety disconnect device, that disconnect switch in the meter would not close back in. So that's basically it. We're open for questions. If you want to unmute yourself, I can probably also go over here. And, let's see. There we go. Nope, no questions up there. Well, I'll move on to our wrap up and review. Why is it important to expose a meter to adverse or real-world conditions in a shop environment? One reason would be to test the meter program to make sure it's logging events like sags and swells. If programming thresholds is something you've had done by the manufacturer, or you've altered your meter program to set up thresholds for what constitutes as a sag, what constitutes as a swell, how many volts is a sag, how many is a swell. You can also set up thresholds for what you consider to be poor power factor, whether that's 0.9 or 0.95 or 0.85. You can set that up and then, drop below and go to 0.75 or something below that threshold and make sure that it's logging that poor power factor, or go to the AMI head-end software and see that you're seeing a 0.9 or a 0.85 power factor, which, exceeds the arrangement you have with your customers based on how they're being billed for poor power factor. And you may have to go to that customer and say you need to install some capacitor banks to compensate for that poor power factor. Same going with the presence of harmonics. You can set up thresholds in the meter or in your AMI head-end software that says if my total harmonic distortion exceeds X level, that it's going to log that event or flag that event in your AMI head-end. You can also do the same thing with the meter. They typically come pre-programmed from the factory with whatever threshold is set up as to what's to be defined for sufficient back voltage so that disconnect switch will not close in. So if I see 10 volts of floating voltage on the load side, it says, oh, that's okay, and that disconnect switch can close back in. If I see 120 volts or 240 volts on that load side and I try to close the disconnect switch in that meter, that disconnect switch should not close because it could get ugly if it did, if somebody has a generator on there or if they're running a power cord to their neighbor's house. That type of thing. You don't want to close that disconnect in because it would not be pretty. You also can have thresholds and or look at the meter head-end software for your AMI and see that the meter logs a loss of phase or a reversed phase on any particular phase of the meter, and then verify that the basic operation of your AMR module or AMI module, that they continue to communicate under these adverse conditions you're subjecting the meter to. It's also, like I said earlier, testing that AMI head-end software to see if the conditions you're exposing the meter to is actually seen by that head-end software. Couple of questions here. They're just more designed for real-world classes as opposed to virtual. And some of them are trick questions, I'll tell you that. And that is basically it. Anybody have any questions?
Boy, Dan, it's a quiet group.
That it is. That it is. So I'm either going to take that as a good sign or a bad sign. So I'm gonna assume the glass is half full.
That's the way I do it.
All right. Well, thank you, Rob and Andy, if you're still out there, for setting this thing up for me. And
I'm still here, and I'd like to add, if anyone wants a copy of this, we'll post it to our website afterward as well.
And my email is on the screen now. So if anybody thinks of anything later or has any questions on the test board I used or on the device I showed for triggering the service disconnect switch in the meter through the optical port, that is a very nice little device to have, very, very popular. And you don't need to use your AMI software. You don't need to use your laptop with an optical probe in the vendor software. It's as simple as can be. It's got 3 buttons. Wake it up, open the contacts in a disconnect, close the contacts of the disconnect. Very, very simple. Anyone can use it. And it takes about 8 seconds to open the service disconnect switch and 8 seconds to close the service disconnect switch. So you can get into that customer, put this thing on the front, and turn off their power and run away before they ever saw you. So you don't run into the unpleasant situations with customers that don't want to have their power turned off. All right, well, that's about it. I still have about 10 minutes. Looks like we may not have any questions here, but if someone thinks of something later on, feel free to reach out to me. I will send this. I modified this PowerPoint a little bit since I sent it to Andy, so I'm going to send her the revised version. And thank you all for participating today.
Thanks, Dan. Thanks, Andrea.
No problem. You're welcome. Take care. Have a good one.
Yeah. Everybody have a good one. And thank our speakers, if you guys are still on. They did a great job on a virtual meeting, and but thanks, everybody.
Thanks, Dan. Thanks, Andrea and Rob, for your help and for everybody participating today and over the last couple of days. Greatly appreciated.
No problem. You're welcome.